All right, recording is rolling. It is Friday, April 26th. We're going to continue on these quantum mechanics journals. I'll give you guys a recap what we've done so far, and then we're going to hit three today, but these are some of the craziest ones from this entire packet. So today's going to be a pretty fun adventure. So buckle up. So what we've done so far, here. You guys remember I gave you guys this list of topics a few days back. We're putting a journal together, just keeping a few notes on each one, in a quadrant of paper. Okay. And these topics kind of closely align with, I gave you guys thumbnail notes. There are these posters hanging around my room a few weeks back. Right? They're printed on the opposite side of the relativity thumbnail notes. Right? So you guys got those. Right? So I'll go through the printed posters I have anyway to recap. It's not a one-for-one alignment with the journal, but it's pretty close. So ultraviolet catastrophe, this is one that's not in your journal, but scientists were playing around with ovens back in the 18th century and realizing that the spectral radiance from these ovens, say like 5,000 Kelvin, was not matching what classical theory would have predicted. So there was a hint there was something amiss. They could maybe classical wave theory was not describing all of electromagnetism. Hand in hand with that, 1887, Heinrich Hertz finds this photoelectric effect that, to say you shine a light on a PV cell, or which I don't think they quite had the kind of the modern equivalent, right? And let's say you're not getting any energy from it. Well, what if you just make the light brighter, right? But then that you got no energy either. Okay, again, that did not align with what classical theory would have predicted. But if you turn up the frequency, then you could get more energy past this threshold frequency. In fact, that was a linear relationship. So if you like double the frequency beyond this threshold, you would also double the energy. And what could possibly explain that? Einstein interpreted this in 1905 as light having particle-like properties, in addition to the wave-like properties that had already been established for light. So now light has this dual nature. Not only is it waves, but it's also particles, right? I gave you guys a garden hose analogy for this, right? So if you like roll marbles down a garden hose, if you roll them with like twice the frequency, right, then you get like twice the marbles. What if each marble represents like a packet of energy? And for electromagnetism, Einstein called those photons, right? That's where photon comes from, right? Won the Nobel Prize for that. Okay. The slope of that curve, here, let's go back to that. This H, whenever you see H for the next week, that refers to Planck's constant. It's one of these fundamental constants of the universe that nobody knows why it is what it is. It's just been observed to be that. And this is the number right here, 6.626 times 10 to the negative 34. And that's joules per hertz, or I could call it joules times seconds, same idea. Right? That's a tiny 10 to the negative 34. That's like one of the smallest numbers you've seen this entire year. Right? Hand in hand with that, since we're talking about quantum mechanics, just that word quantized, we're talking about like quantity. Is the universe in some sense pixelated if you get small enough? And this is the physics of really tiny things like atomic size and smaller, right? And yeah, you're going to run into these limits. Right? This is Planck length, where it doesn't really make sense to subdivide it, right? And this is Planck time. Now, mathematically, you say, well, we could have half of that and a quarter of that, but physically, there's really no such thing. So, in a sense, the universe is somewhat pixelated, right? Right. Now, if light has this dual nature of being both a wave and a particle, along comes this guy named De Broglie, says, I wonder if this could apply more generally to other types of particles too. So he takes the physics that's lying around at the time, beginning of the 20th century about, and makes some substitutions and comes up with this wavelength of a particle. Right? Now, so it takes Planck's constant, which is already a tiny, tiny number, divided by the momentum of a particle, and there's an associated wavelength. Could that be, right? What could that represent? What consequence could that possibly have? Well, how about the entirety of chemistry, right? All chemistry and chemical reactions and electron configurations and why atoms look the way they do. Right? Right, so this electron configuration, right? Electrons only orbit the nuclei at certain set locations, right? Rutherford figured out the structure of an atom. Said, okay, we got this dense positive nucleus and this shell of electrons. Right? But electrons going around, they can't just orbit any location. Like a planet going around a star could be at any location. That's fine, right? But not for electrons. There's only certain places. Right? Why can that be? It's because electrons have more wave-like properties than particle-like properties, and they have to complete their wavelengths going around. So like if you make a paperclip chain, you can put 4 paper clips or 5 paper clips, but you can be like 4.5. Right, so there's like these incremental values they could like these discrete values that electrons could exist at. Right? And that's going to bring us to I think this is the last one we were doing yesterday was Schrodinger's equation, right? So this is how do uh, particles like uh, electrons, for example, even exist? Well, they exist probabilistically, like all spread out. This is one of the reasons that we took a few days to do probability and statistics. Okay? Now, when we were doing probability and stats, I gave you guys some normal distribution curves. Now, this curve right here is not a normal distribution curve, but kind of the idea goes over, right? So if you want to say like, where is an electron? Right? Oh, before you measure it, you can only say probabilistically. Now that's different from anything we've done in the class so far. Like one of the first labs you guys did in this class way back in the day was rolling Hot Wheels cars down inclines. And you could describe precisely with equations, like where is the car going to be at any particular second, how fast is it moving, and how much is it accelerating. Right? But really tiny particles like electrons, not so much. You can only say, well, there's like some percent chance they're going to end up here. Maybe it's like a probability curve, right? And some percent chance they'll end up like here, 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 right? Now, when you make a measurement, interestingly, this wave uh, equation collapses to just one reality, and then bam, right now the electron trace is like right there, right, and now it actually is there, right, and then this whole thing resets, so this whole peak like shifts like over there, because that's centered over where the electron now is, right, and then this spreads out with time until you make another measurement, and then it collapses to like bam, right now the electron's like over here, bam, right, and so if you made like 1,000 measurements, then you could put a bar chart together, which would create a curve that looks something like that for Schrodinger's equation, right? Right, that's about where we got. Right, so you guys ready for new territory? The next one lined up is actually, I'm getting a little ahead of myself. Right, gonna play you guys one video before we get to Heisenberg. That's what we're gonna do. Switch my screen over here. All right, so a little bit of recap, and then Heisenberg we're gonna go to. All right, so you guys saw a little bit more, talks about battery conditions, but all right, you guys get that. So good recap there. All right, Heisenberg uncertainty principle. What is that? Heisenberg. Yeah, there you go. So here's a poster for that. Right, there's the equation written out, right? Where delta x is uncertainty in position, delta p uncertainty in momentum. Right? Remember, momentum is mass times velocity. Sometimes you see it this worded in terms of like you cannot precisely know both the location and the sometimes velocity of a particle simultaneously. Right? Now in macroscopic classical physics, that's not a problem, right? You can watch your Hot Wheels car go around, you can describe things precisely, right? Like how precisely can you measure? Well, it just depends on your measuring tool. I can go like centimeters or millimeters, whatever, right? But when you get down to atomic scale, you're going to run into this uh, this limit, right? This is just like baked into the fabric of the universe. Right? So here's what I might put in this quadrant, right? Here I got a Heisenberg uncertainty principle written out here. Right? I've got these posters hanging around, so here's this poster right here in front of me. Uh, and then here's the experiment he set up to show this. So he was firing photons, or he had a laser here, through the slit size delta x, right, for some uncertainty position where the photon could possibly be, right? And as that gets too narrow, then you're getting too much precise information about what delta x is, right? While you guys are copying that down, I'm gonna label these two. So delta x I'll call uncertainty in position. Delta p I'll call uncertainty in momentum, right? And then h on 4 pi, right? Oh, well, you guys remember h, that's Planck's constant. It's like 10 to the negative 34. Ooh, okay, already, that's crazy tiny number. Divide that by 4 pi, now it's only even smaller. Okay? So this is just a tiny constant. Right? And then, yeah, in our everyday experiences, we're never going to get close to running up against that. It's crazy you could even set up an experiment where it was shown that you could run up against that limit, right? Kind of like theory of relativity back a few weeks ago, right? So like if you hop in your car and drive on I-95, does time dilate a tiny, tiny bit for you so your clock beats differently than somebody who stayed at home? Yeah, but it's such a small amount that unless you had an atomic clock, you wouldn't be able to really measure the difference. Okay. All right. It's Heisenberg uncertainty, right? There's an actual like limit to like, how precisely we can know anything, right? Exactly where is a particle and what is its momentum. Right? All right, you guys ready for a double slit experiment? Double slit. Right. Right, so set up double slit experiment. It's actually kind of two versions or two versions of this. The classic 19th century version is just very simply if you take a card and you cut a couple of slits into it and then shine a light through, you can see an interference pattern on the other side. Right, that's what led scientists to say, okay, well, light clearly has wave-like properties. Oh, light must be a wave, right? Until, of course, Einstein comes along and interprets the photoelectric effect as light also has particle properties, right? Okay, so that's the basic double slit experiment. Right? But there is a quantum mechanics addendum to this, which is, okay, well, here, I'm going to play this video. This gets really crazy. You guys ready to see something crazy, crazy? All right, so flip over here and find double slit experiment. Got it. All right, so that's not crazy so far. All he's doing is he's establishing what is the definition of a particle, what is the definition of a wave, right? So now we know what to look for that would distinguish one or the other, right? But you can probably see kind of where this is going is, well, yesterday I sure talked a lot about duality, right? Like light has this dual nature, maybe electrons now have this dual nature, they're kind of particles, but wait, actually, they're actually more like waves. But hey, now we have a test, right? Now we have a test we can really see if something a particle or wave. Right. Even that, I don't think it's too crazy at this point because okay, yeah, electrons are more like waves; they exist probabilistically. Yeah, it could go through both, interfere with itself. All right, right. The crazy part is what's about to be coming up next. Right, and that's the crazy part right there. So, like all the labs have done this class so far, you can build some model of the universe. Let a Hot Wheels car go down an incline, let a pendulum swing, and you can assume that you can be a neutral third-party observer and make some measurement data, right? But when you get to particle physics and quantum, having measurement data, having observational data, right, actually affects that reality. Right? Tree falls in the forest, does it make a sound? Well, last week that was a maybe a crazy question. Like, of course, it makes a sound. There's a crash and there's a really spin, right? But now it's like, right? Uh, what does an observer have to do with like affecting reality, right? There's extension questions on this, like, does reality depend on there being a conscious observer? Does conscious observation affect create the universe? And that comes out of this experiment. I do want to give you guys a little bit more sophisticated version of this because here they got this cartoon eyeball to represent some kind of observer. But where's like a better version? Here we go. Here's a better version of this one. Right, so this is a kind of a long one. You have to watch like 5 times for it to start to make sense. But one thing he does, he recommends you watch that video I just showed you guys, right, to get the big picture idea. Right? And oh, hey, look, he's got a laser. He's firing photons through 2 slits, slit A, slit B. Right? And then now there's no cartoon eyeball here, but in place of that, he has lots of beam splitters and mirrors where these beams can bounce all around different ways until he reaches this coincidence counter. And then depending on which path these photons possibly took to reach the coincidence counter, right? You can have that data effectively as to whether it went through specifically one or whether it's ambiguous. And anytime it follows one of these paths that ends up being ambiguous as to where to go through, go through one or both the other, you always get an interference pattern. But if you follow one of these paths where you can determine, yes, it went through either only A or only B, then you always get just the bands, right? Which would indicate like a particle, right? So just having that information about did go through one or the other, right? Having that observational information, right, actually affects the reality. Does it make it more a wave of potentials, right? Like a probability function, like Schrodinger's equation, right? Or does that probability function collapse to just one reality? It goes back to behaving like a particle, right? So here, I got set up a couple of cards here. Let's put 2 slits here. All right, you guys have rulers on your desk too, so I'm going to put 2 slits, 2 slits. All right, so I got this experiment set up twice. Right, one I'm going to do without an observer and one with an observer. Okay. All right, I'm firing electrons through. So let's do electron, got to fire through. Pew! Right, and same thing here, electron, fire through. Pew! Okay. And say without an observer, you get an interference pattern, right, which indicates a wave, right? So let's draw an interference pattern back here. Here's the back wall. Right? You might see, right? By the way, if you look really close on that Heisenberg uncertainty video, for that Veritasium video I showed you guys a few minutes back, right? Even when he was doing the single slit experiment, and the light was like spreading a little bit, there actually was a little bit of an interference pattern there too, right? So interference pattern for wave, right? But with an observer, and I'm gonna again draw a little cartoon eyeball to represent the observer. Okay, so here's your observer. So with the observer, the particle behaves behaves like a particle. Right. Doing electrons here, you can do electrons, photons, same idea, right? Right. If you have that observational data about which slit didn't have to go through, it actually changes its nature. It goes from like one thing to acting like another thing. Okay. Right, so while you guys are finished with that, I'm going to set up this next one, which is measurement problem in Schrodinger's cat. Because this measurement problem, now we got this problem with measurements, right? Now, just the act of observing and measuring, you can no longer do a neutral third party observer anymore, right? Now you're like reaching in and like changing reality just by making that observation, right? And there's this really famous, crazy thought experiment that I'll show you guys called Schrodinger's cat. You guys remember guy Schrodinger with Schrodinger's equation? Says, okay, things exist probabilistically spread out until you make a measurement. He was looking at the physics that was emerging at the time. It's like 1920s, 1930s, saying, this stuff's getting so crazy. There's no way some of the stuff could really be real. And if you think like a scientist, what you try to do is come up with experiments that could poke holes in things, disprove hypotheses. That's one of the first things you guys learned this, or emphasized in this class way back in August, was scientific thinkers, you really try to disprove hypotheses. Right? So he tries to do this with this next thought experiment called Schrodinger's cat. Right? Now, I should tell you guys, nobody's actually ever done this experiment. It's kind of like an undoable experiment. It really only exists as a thought experiment. But switch over and let's watch this video and then fill in some details. All right, where's Schrodinger's cat? Ooh, crazy. Right. Right, so back over here. Here's the poster version of this right here. I'm just gonna more or less copy this into that quadrant. Okay. Right, so you got this closed box, right? This closed box. I got this set up right here. Let me zoom in where you guys can follow along with me, right? So I got a closed box, right? Closed box, right? Closed meaning that this observer on the outside, which I'm going to represent with this eyeball right here. So little cartoon eyeballs back. This observer, right? Cannot see what's going on inside the box. Has no way of detecting anything happens inside the box, right? So as long as you're not observing something, right? Well, for particles, remember particles exist probabilistically. That's back to the Schrodinger equation here, right? Like where is the electron? Well, it's spread out all over the place. It exists probabilistically, right? Now Schrodinger connects that quantum world to the macroscopic world, shows like this crazy, like almost wannabe paradox, right? Let's say we have this radioactive particle. Now radioactive particles have some half-life associated with them. So there's a 50-50% chance after that one half-life that they decay into something else. Now, some radioactive particles decay after like a tiny fraction of a second. Other radioactive particles, it'd be thousands of years before there's a 50-50 chance. For example, one of them we're going to look at, there's an isotope of carbon called carbon-14 that will eventually decay into nitrogen, but it has a half-life of 5,700 and something years. So it takes that many years to have a 50-50 chance of decaying, right? Let's say just for the story that there's a radioactive particle, radioactive atom has a half-life of like 1 hour. So every hour you go back and check on it, and there's 50-50 chance after an hour that's decayed, 50-50 chance that it hasn't, right? You put that in the closed box, right? Now that radioactive atom, let's say it's tied to the system, where it's gonna trip this hammer, which is gonna break this vial of poison, right? So it's got a little flask going, little skull and crossbones right here, right? It's a vial of poison, right? So that once this radioactive atom decays, it's going to break the vial of poison. Right? There's variations on this too. You'll sometimes see a version of this has gunpowder or something. Anyway, so the entire time the box is closed, this all state of superposition, right? Has the vial been broken or not? Well, you cannot definitively know that until you observe it. And before you observe it, that reality is only ever probabilistic, right? Now you throw in the cat, right? And what that means for the cat then is the cat is now in also a state of superposition of being both dead and alive, not dead or alive, but dead and alive simultaneously. It's a state of superposition, right? Now, as soon as you open the box and make the measurement, make the observation, that probability wave now collapses just one reality. Now the cat is either dead or alive once you're observing it, right? But the entire time that the box is closed and you have no way of knowing what's going on inside, right? Everything is only ever probabilistic because that macroscopic world is tied to that quantum reality. Okay? And oh yeah, go.
Well, what if there was a person in the box?
Yeah. What if there's a person in the box?
And nobody else.
Right. Yeah, well, you're getting to the question, like the bigger questions that kind of emerge from this, right? Like, what gets to have consciousness? Is the cat's conscious, right? Or is that an observer, right? What about observers and observers? What about consciousness and consciousness, right? What about the entire Earth, right? Does there have to be some outside observer on Earth, or is it okay for all observing each other? What if you have two cats inside the box, right? Yeah. So this is really only kind of like locked away as a thought experiment. This is something you can never actually really do, right? Right, but it's an interesting, I guess, consequence of this probability function. Right, that's our pause point today.